Hey, minasan, konnichiwa, Zamurai Engineer desu. So in this video, let us do the next example, problem solving E003. This is about design of a moment frame by DAM or DAM. Okay, so given, we have a figure below. The uniform load, WD, includes beam self-weight, an allowance for column self-weight. So beam self-weight and allowance for column self-weight. Use direct analysis method, DAM, direct analysis method. All are A992 material. So required, find the required strength and effective length factors for the columns. So now I am currently sketching the required figure, the given figure. So this type of sketch is what we call W. So W, this is the W symbol, no? W frame, W beam, W type of cold rolled material or hot rolled material. So W type. I will do it like this. Freehand. Let's try. And so how many? I think there are about 1, 2, 3, 4, 5. So 5. So 5 columns. Another 2. Okay, so last one. So assuming that the drawing is beautiful and straight line. Okay. Let's this our event. So what you can see is pin connection, pin connection, pin connected at the bottom. So we have what? Beam, which is connecting the column. We have the beam, and also the beams are what? W type. So W type beams, and they are roller connected. So roller connected. So this is also W type. Look, in W type, the drawing is like this because this represents flange. This is flange. This is the web. The middle portion is the web. So let us connect the next one from the other. So flange at the bottom. Okay. So take note. This second bay, the second bay is connected fixed. This is roller connected, fixed. Next one, they are also roller connected. So ruler. Another beam. So ruler and ruler. Okay, so we have all the information. So let us draw the grid. I am drawing the grid right now. I'm drawing the grid. Okay. So the grid, I will label the grid. So I am labeling the grid. So this is what we call grid. So vertical grid, we will label letters A, B, C, D, and E. Okay? So also, we can use the grid in order to reflect the dimension. So let us reflect the dimension from this. We have what? 30 feet. Okay? 30 feet. 30 feet and 30 feet. Okay? So 30 feet is less than 10. So that is about 9 meters. Okay? So 30 feet. So 9 meters, 9 meters, 9 meters, 9 meters. So that is about it. So we have what? Sa center of the column up to the extreme center of the column, we have what? We have the load. So we have what kind of load? This is uniform type of load. Uniform type of loading. As also indicated in the problem narrative. Okay. Uniform type of loading. Wherein we have what? WD is 0.4. Okay. KIP per foot. And also WL meaning this is WD dead load, lead load. So this is W meaning uniform. Sorry. This is 1.2. So this is wrong. This is actually 1.2. 1.2 kip per foot. Okay. So this is 1.2. Okay. So what are the material? W18 by 40. This is the dimension and this is the weight. Okay, 40 is the weight. So and for the column W12 by 65. For the column we have here W12 by 65. Okay. And what about the height? So the height is from this point up to this point. So this is the lowest portion of the column and this is the center of the beam. So this is what? Our height, which is 20 feet. Okay. Okay, solution. So let us solve. Solution. So maybe we can solve this at the same time. So let us go to the table of AISC. So table for what? Table 1-1. Okay. So where is the table 1-1? Table 1-1. Where's the table 1-1? Table 1-1. So let us go to the 360. Let's go to the 360 and try to find the table. Let's find the table 1-1. Because we want to know the properties of W12/65, the column. We want to know the properties. So we need information about the properties. Like what? What do we need from the properties? For example, the area. Okay. So W12/65 because this is the column. Okay. And we want to know the strength of this column. Okay. So what are the properties that we need to know from this? From the table, for example, area. Okay, what is the area? So since we are using English, so we will have what? Inch squared, square inch. Okay. So, okay, na-open na yung aking ano. So, let's just go to the table 1-1. Material. So, page okay, so I will share so that you can see what I'm doing. So I am searching for the table of values. I'm searching for the table of values here. So this is the same thing that we used a while ago. Table this is table what? Table 4.1. This is what we are looking for. Section. We want to know the section of this particular so this is not the one. It's not the one we are looking for. So tables. Where are the tables? Handbook of tables. Properties of structural shapes. So maybe this one. So okay, the properties of the structural shape. This is angle. Aha. Let's go to the W. Okay, let's go to the W. So W12. So this is W12. So here, as you can see, W12 by, there is no W12/65, W12/50. So this is not the one. So as you can see, W12/50. Okay, so there is no W12/65. Why? Oh, this is not the one we are looking for. This one. So as you can see, what are the properties that we can find out? Area, depth, weight per foot. So weight per foot is 50. As you can see, if we have W12 by 50, 50 means the weight here. Oh. So you can see 50. Can you see that? 50 is the weight. 12 is the, what is the 12? 12 is the depth, so nominal depth. So you can see here depth in inches, but we want to use the actual. This is the actual depth, 12.2. But it is nominally called 12. So meaning to say, if we have, in our example, 12 by 65, we have 12 as the depth. Depth of the meaning the flange to flange length, the height of the beam, okay, or the column, okay, the height. So what do you mean by that? Here, I will draw it. So I will draw it. So we have a flange like this. Flange to flange distance. So if we want to determine this, this is what we call 12. So 12 inches. Okay. So that is 12. So in actual, that is 12.2 according to this table. So this table is not complete. This is incomplete because there is no 65. But we can use what? Interpolation. We can use interpolation to find out what is 12 by 65. Okay? So we can use interpolation, or we can look for another table. Okay. Another table, let's find out it. Structural steel shape. So this is what? S-type. This is the S-type, C-type, C-type, L-type or angular type, T, Z. So where is the W type? There's none. There's no W type. So this is tubular. This is tubular. So where is the W type? S type. These are S type. So again, there's none from this. Okay, let's open this another one, another reference. So W, these are W type. So let us look for the 12. Okay, so W12. So W12 and 65. We have W12 65 here. So the depth is 12.12. So we have H. This is H. So H is equal to 12.12. Okay, 12.12. Is it okay? 12.12. Okay. Inch. And the area is 19.1. So 19.1 square inch. Those are some of the, there are many things that you can look up from the table, but currently we are just looking for area and the height. Okay, so after that, okay, find out from the table, okay, from table, okay. So the beams from grid lines A to B and C to E, okay, are pinned at both ends and do not contribute to lateral stability of the frame. Take note. Take note. So let's go back to the shear. Okay, so to our spotlight. So the beam, this is the beam from A to B, C to D, and the columns at A, D, and E are pinned at both ends. So pin here and pin at the top. Pin and pin. Pin and roller are the same. Pin roller are the same. We call this pin. Okay, pin here and pin there. Pin here and pin at the top. So A is pin, pin at the top. So do not contribute because of that. Do not contribute for the lateral stability because it is not stable. It will just what? Rotate. Take note, pin connection rotate. Okay. So therefore, there are no, because of that, there are no P delta capital effects to consider in these members. Okay, so P capital delta is 0 at A, D, and E columns. Okay, so we cannot consider anything. Okay, so we can design those things as, okay, so we can use what? We can use C is equal to L. Okay. Okay, next, the moment frame between grid lines BC, the moment frame. What is the moment frame? This whole thing, this is the frame. The frame is composed of two columns and this beam. So because this is fixed, and this is pin, because of the fix here. So this is a system, a frame that will contribute to moment. No? Okay, so because it will resist moment here. No? So therefore, is the source of lateral stability. So that moment frame is the source of lateral stability, and therefore will be evaluated using the provision of Chapter C of AISC specification. So I think now open na natin siya. No? So I think we'll. Okay. Although the columns at grid lines A, D, and E do not, okay, contribute to lateral stability, the forces required to stabilize them must be considered in the moment frame analysis. The interframe, a grid line from A to E could be modeled. Okay, so from A to E, so interframe, because the whole frame will resist moment because of this fixed connection. Okay. In which the stability loads from three leaning columns are combined into a single representative column. So for simplicity, we can combine A, D, and E. Okay. So because of that, we have the following: maximum gravity load combination. So load combination. From our study of load combination, from load combinations, we have what? AISC. So let's share the load combination of AISC. Let's look for the AISC. AISC here, no? Okay. So load combination. Okay. So from this load combination, as you can see here, we can say that so maximum gravity load combination. Gravity, because more on self-weight and so, and the given WD and WL. So therefore, we can say, so using LRFD, so using LRFD, so we'll have the following. So ultimate, therefore, is 1.2. I said it a while ago that the dead load must be multiplied by 1.2 plus 1.6 times live load. Okay? So because of this, we can just multiply. Dead load is this one. So let us add dead load is 0.4. So 0.4 and live load is 1.2. 1.2. So multiply. So let us use the calculator. Okay, using the calculator. So this is what? 2.4 kilopounds per feet. Okay. So this is how we solve it. LRFD. LRFD meaning strength design. This is the strength design. So this is strength design method. Okay, strength design method. Okay. How about the other